before you start the lecture, let's talk about the midterm. I know it's not an interesting topic, but we have to talk about it. So I was thinking about next week on Thursday, we can have our midterm, or I'm hoping also to Tuesday the week after. So whatever you guys like. So you guys need 1 week to study for the midterm, or like 10 days to study for the midterm. So okay, Tuesday.
Yeah, 10 days.
Tuesday, 10 days.
Yeah.
All right. So the midterm is gonna cover until the lecture on Tuesday next week, and we're not gonna have much. We're gonna almost finish most of the stuff needed for the midterm. Maybe we are gonna solve an example or something next week. So so mainly the midterm is gonna until the lecture of today. Next lecture is gonna be more of applications. The midterm is gonna cover. Did you guys see homework too?
Yeah.
Okay, so I think something happened. I upload homework 2, but maybe I didn't publish it. So when did you see homework 2 on Canvas?
Yesterday.
Yesterday? Oh, okay. So the thing is, I think I uploaded like maybe 10 days ago, but I forgot to hit publish. So I believe the deadline might be closed for you to finish it.
Yeah.
So maybe I would, like, until the midterm, like, you have another 10 days until you finish the homework. Or maybe let's say, yeah, like let's say another week. Is that fine? Like until Thursday next week. All right. Okay, so I'm gonna extend the homework. All right, so we're having midterm 10 days from now. Just get prepared. I would recommend reviewing the notes. That's number 1, like to understand the concept. Number 2, solving, like understand the problems that we solved in the lecture and the problems in the homework. If you do this good, the midterm is gonna be easy. If you understand them, like if you solve the problems by yourself, I mean, I'm fine if you check your answers with your classmates, but you have to understand your answers, like that you know everything that you have written in your homework solution, that you understand all of it, okay? You are allowed to use one sheet. You can have like one sheet. You can write on the front and on the back. You can put whatever equations that you like, and you can get the exam with this one sheet. You can put whatever formulas you needed for this exam. Is that good? All right. Okay, so last time we started talking about the distributions, and if you guys remember, here, and by the way, most of the distributions that we have talked about is what we call them continuous distributions. So there's continuous distribution, and there's discrete random variable distributions. So if the distribution is like a function, that's continuous. But if it's like steps or something like at specific points, that's discrete. So normal distribution, standardized normal distribution, log normal distribution, or standardized log normal distributions, they are all continuous distributions. There's other distributions can be used for events that are discrete and not continuous. Like, I don't know, when we talk about 100-year event, that's a discrete, because you have multiple events at discrete time. But if these events are many, there are many of them, like there are a lot, like we are talking about 1,000 events. These events, if we put them together, they can make the function more towards a continuous function. So when you have a discrete, like random variable, but you have a lot of numbers and you have a lot of data about it, you can convert it to, the summation can be an integration, okay? All right, so if you guys remember, we had the normal distribution. And for the normal distribution, we said that you might have a mean, like let's say mean and standard deviation, like x and x, like let's say that this is 8 and this is 1. That's the normal distribution. And we had something, it's called standardized normal distribution. For standardized normal distribution, is something similar to this one, except that the mu x and sigma x are different. Mu x is 0 and sigma x is 0, and we have tables to solve this one. This one, its function is, if you guys remember, the PDF of this distribution is fx, let's see if I memorize it, it's 1 over sigma x root 2 pi multiplied by the exponential of negative 1 over 2 of the random variable, let's put write fx of the random variable x. That's actually, by the way, it means that the probability of x is less than or equal x. We all know that. So here we're gonna have x minus mu x over sigma x squared, something like this. That's the function of the normal distribution. And I told you that there is no closed form solution to the fx. If you want to find fx of x, you have to integrate this from negative infinity to the variable x that you are looking for. Let's say that this distribution is something like this, and you want to find out the area under this curve, or what is the probability of your random variable to be less than x. This is not going to help you. You have to integrate this function from negative infinity until this number. And that's what we call the CDF. So that's the PDF, and that's the CDF. And I have to put all these under the integration. I have to put 1 over sigma x root 2 pi, the exponential, and then I have to put everything inside the exponential, sorry.
What's the reason that there is no solution for this equation?
Because that's not, like, sometimes when you do integration, there is no way that you can integrate this function. There is, like, there's people trying to like expand it and make it a polynomial and all of these stuff. It's kind of close, but not exact. So some integrations are solved numerically, and actually that's an application in the seismic engineering. Like when you have a seismic load, if you guys remember, like the seismic load, the ground acceleration is something like this, right?
Yeah.
The ground acceleration over time, the earth is shaking, the ground motion is keeping changing over time randomly, like something like this. So there's no closed form function for this. So that's why when you have your equation, your equation like the one that has mu double dot plus cu dot plus ku equal to negative mag, or the forcing function ft. If ft is something like this that you cannot put it in a closed form, when you integrate, because this is a partial differential equation, and you need to integrate it to get u, right? So the thing is, you can't solve this numerically. You have to divide it into small pieces and solve it numerically. Okay? So that's happens sometimes when there's no closed form solution for the function that you are integrating. Okay, so getting back here, so that's why, but the thing is, this one, it's still difficult. That's why they like convert it to standardized normal distribution, and they try to solve it to make it easier. Like for standardized, I told you that mu x and sigma x equal to, mu x is equal to 0 and sigma x is equal to 1. If you put mu x here, 0, and sigma x equal to 1, so you reduced it a little bit. This is gonna be x by itself. But the thing is, to do this, we say like u is gonna be equal to x minus mu x over sigma x. So, and then I'm gonna remove this and put u. Alright, so that's gonna be a standardized normal distribution, which is gonna be equivalent to, like if you put here mu x equal to 0 and sigma x equal to 1, so it's gonna be only function in x. It's gonna be x squared. So this PDF is gonna be something like this, 1 over sigma x, sorry, the sigma x is gonna be 1, so I have to, like when we put, because we have here sigma x is equal to 1, so this is gonna be 1, and you're gonna have 1 over 2 pi, and this is gonna be the exponential of negative 1 over 2 u squared. That's a little bit easier function. It's okay? So that's that standardized normal distribution, where u is equal to x minus mu x over sigma x. That's how we convert it. Okay, so if I give you a normal distribution with mu x and sigma x, the thing is if you kept it that way, you will not be able to solve it. So we have to convert it to a standardized normal distribution because we have the numerical solution of this function, but we don't have the numerical solution of this function. So if you want to integrate this one, this integration is going to be like the f, since we put this u, this is going to be u. And this is going to be not x anymore, this is going to be u small. And the f capital U of u is going to be the integration from negative infinity to u 1 over root 2 pi the exponential of u squared. And here you're going to have du. All right? So this one is the one that we have the numerical solution for, the one that we have table to, and sometimes we write it phi of u. It's going to be equal to the same thing. And this one is phi small of u. That's where we have tables too. And we talked about like it has mean equal to 0, and this is our function, something like this. And if you have here negative u1, and if we have here u1, the phi of negative u1, which is this area, is going to be equal to the 1 minus the phi of u1. The phi of u1 is all this area. If you subtract 1 minus this area, is going to get you this triangle, right? We have done this last time. So I just like want to confirm this background with you before I move to something new. Yeah, also, yeah, that's the same thing. Like we also put here phi of negative u1 plus the phi of u1 is going to be equal to 1. The thing is, this part plus this part is going to be also equal to 1. Or I can send this to the other side with the positive, it's going to give you the same function. Does we all understand this? Okay? And this is the one that we have the this for. Okay? So this numerical table is not the solution of the normal distribution, the solution of the standardized normal distribution that has u to the power square here. Okay? All right, so let's solve another problem. I know we solved a problem last time, but let's solve another one just to make sure that we understand the concept very well. All right, so I have an example that says that in a compressive strength testing for a normal concrete after 28 days, the sample mean, like after we were testing concrete, we have the concrete blocks and take them to the lab and we were testing them. And after we tested them, we took the average. And mu was 36.8 Newton per millimeter squared. And the sigma, or the standard deviation, was equal to 5.3. All right? Newton per millimeter squared. That's from the standardized testing of the compressive strength of the concrete block. Okay? All right, so what I'm asking for here, I'm asking what is the probability of the concrete compressive strength to be, let's say that the concrete compressive strength is x, that's my random variable. What is the probability of this x to be more than 30 and less than or equal 45? That is what I'm looking for. Okay? So it's like, okay, you have 100 concrete blocks. You take, I don't know, like you take 50 of them, and these 50 of them, you tested them. Or maybe the whole 100, and you tested them, and you got the mean and the standard deviation of them. So if you pick one of them before the testing, I want to know what is the probability of this cube to have a compressive strength between 30 and 45. Okay? All right. So the first thing, this is a normal distribution because I give you mu and standard deviation in a normal distribution way, like they are not 0 or 1, so this looks that way. And the thing is to solve this, okay, so that's how it looks like. I have, this is the normal distribution, not the standardized one, and I want you to find out, and the mean of this is 36.8, and I want you to find the probability 30 and 45. That's normal distribution, not standardized normal distribution. The thing is, I want to convert it to a standardized normal distribution that is going to be that way. The thing is, this is going to be 0 because we know that the mu is always equal to 0, and we need to find out what is the value here. The value here, the equivalent values to 30 and 45. To find the equivalent value of 30 and 45, so you want to get u1 corresponding to each x. So what I'm going to do here for 30, I'm going to get u1 is going to be equal to x1 minus mu over sigma. My x1 is 30, and here my mu is minus 36.8 over 5.3. That's u1, which is going to be here. u2 is going to be x2 minus mu over sigma, and this is going to be equal to 45 minus 36.8 over 5.3. And then I get these two values. This is going to give me negative 1.9, 1.19, and this is going to be 1.55. So I have here, this is negative 1.19, and this is 1.55. Okay, I want to find what is the probability of my compressive stress to be in between these two numbers, which is equivalent to these two numbers. Okay, so in real life, that's the numbers that I'm looking for, but I can't solve this one, so I transform it into an equivalent one that I can solve it. So basically, if I got phi of 1.55, it's going to give me all this area. And if I subtracted the phi of negative 1.19, it's going to subtract this area, and then I'm going to get this one. So if you want to find the probability of your compressive stress to be more than 30, and less than or equal 45, that is going to be equal to the phi of 1.55 minus the phi of negative 1.19. What does that mean? That means that phi, when I say phi, that means this table. Because this table is the phi table or the u table. Sometimes they call it the z table. So sometimes we call it phi, z, or u. They are both represent, or all of them represent the standardized normal distribution. So if you find the phi at 1.55, that means that what is the probability of your random variable to be less than 1.55? So it's going to include all the area until negative infinity. But I'm not interested in this. I need to truncate the area that is less than negative 1.19. So that is going to give me the phi. So phi minus phi negative 1.99. Then I'm going to use the tables. If you use the tables, here 1.55, that's positive. So I'm going to come here, I'm going to go all the way down until I stop at 1, and then I'm going to go all the way here until I get 0.05. And actually, if you want a 1.55, oh sorry, I go down until 1.5, and then I go here at the other 0.5, so this is going to give you 0.9394 minus negative 1.19. The negative is the other side. So negative 1.19, I have negative 1.1, and then I have 0.9 is the last one, so this is 0.117. And this is going to be equal to 0.8224. By the way, actually, you can solve this problem with 1/2 of this table. Do you know that?
Yes.
How? Like if I give you not the two sides, I give you only one side, 1/2, there is a way that you can use 1/2 because you know that they complete each other. Okay? Like you wanna find, okay, usually sometimes in closed book exams, they give them only 1/2 of the table, like the positive one. The positive one is gonna give you 1.55 easy. But how about if I have a value that is negative? We get 1 minus the value that is positive. So that's if you have if I didn't give you the negative side, you are gonna get the positive side, like you are gonna get 1.19 positive. So it's gonna give you all the area here. So if you subtract 1, you get the other side. So that's also one way to do it. Okay, so right now we have the probability of getting your compressive concrete stress between 30 and 45 is 82%. Okay, all right. With this, let's shift to another distribution, which is another important distribution. It's called log normal distribution. For log normal distribution, usually your function is x is equal e to the power y. If your function is like this, that means it's follow like your x is a log normal variable. X is log normal. But y is normal, like y is normally distributed. And let's say like you take len to both sides, like you take len x. Do you guys, if I take len ey, do you know what it's gonna be? It's gonna be equal to y. So this y is normally distributed. That's one of the characteristics of the log normal distribution. So basically y equal to len x is a normal distribution. So let's give it a little bit of a look here. Like let's take an example. One of the most interesting examples of the normal distribution is that log normal distribution is like a skewed normal distribution. It's like something, but it's all positive. Like it's something like this. Let's say this is x, and this is fx of x. It's something like this. Something like this that has a little bit of a skew to the end. This is something like the income of the US citizens. Like most of the income of the US citizens is something around here. But there's a lot of rich people that their income is all the way here, that they get billions or millions of dollars, but most of the people is like average people, less than $100,000 is like something like here. So that's is a log normal distribution. Why? Because it's not symmetric, okay, and it's all positive, and it's skewed towards the x. The thing is, we need to convert this to a standardized normal distribution so that we can be able to solve it using the same concept and the same table that we have over there. So the thing is, to do this, we take the len of all the values here, like you have a bunch of values here. If you take len x to these values and try to grow here's not x, here's len x, which is y equal len x. and take len for all the values. If you try in your home and you take the len of $100,000 and the len of 5 million or the len of 100 million, the len make the numbers smaller. So they shrink the numbers to be like something, it's gonna be something like this, and they tend to be normally distributed, like something, you will find them something like this. Once you take the len of all the values here, you can build it yourself. Like you can try it yourself and take the len of numbers at the back, like very huge numbers. You are gonna find the difference rather than being millions of dollars. The difference is gonna be very, very small when you take the len. Okay, so this is gonna be f y of y. So this is log normal, this is a normal distribution. Okay, so let's put the general equation of a normal of a log normal distribution. So this is gonna be equal to the fx of x of this distribution is equal to 1 over x xc root 2y multiplied by the exponential of negative 1 over 2 len x minus lambda x over xcx. All this is squared. That is the BDF of the log normal distribution, the BDF. Okay, so we have two new variables here. We have lambda x and xcx. Lambda x and xcx are still the mean and standard deviation, but the mean and standard deviation of the log normal distribution, this one. This one. So that's what we call logarithmic mean. And this one we call it logarithmic standard deviation. Okay? All right. So the thing is, if we got to the mean here, like our random variable in this one is something like this, len x. That's our random variable. We keep putting it that way. If you got the mean and the logarithmic mean and the logarithmic sum, because every number here is a logarithm of the numbers that are here. So their mean is something like this, their standard deviation is something like this. So usually in the problems, I will give you the mean numbers of this one. Okay? Like I would give you like mu and sigma. The thing is we need to convert mu and sigma to logarithmic mean, like this is mu x and this is sigma x. We need to convert them to logarithmic mean and logarithmic standard deviation so that we can start solving this problem. But the thing is, there's no closed form solution for this one. Still, I mean, like I can't integrate this one. Like I want to find out. Okay, so I want to find out the CDF function, the fx of x. To do this, I have to integrate this from. That's why, okay, this function is going to be 0 because the logarithmic function doesn't start from negative infinity. The logarithm is always positive. There is no logarithm for the negative value. So this is always going to be the integration from 0 to the x that you are looking for, and then you are going to have 1 over x multiplied by xc. By the way, this function is similar to the one that we have in a little bit for the normal distribution, except that you have x down here. Because before I used to have sigma, and this is xc, like the corresponding standard deviation for a log normal distribution. And here I have lambda, which is the mean, and here I have xc, which is the standard deviation. So the only new part is you have 1x down here. Right, so I have to integrate this function from 0 to x to find the probability. That means that's the probability of x to be less than a specific value. And here I'm going to put the exponential of len x minus lambda x over xcx, and then you're gonna have here dx. It's the same thing. I want to convert it to a distribution that I have answers for, which is the u distribution or the phi distribution. So we can tweak the variables that we have here a little bit so that we can do that. We can also say that u is going to be equal to ln x minus lambda x over xcx. If we make u equal to this, the thing is I want to find du because I need to convert the dx, this dx to du. So if you take the dx to this thing, this is going to be equal to du dx. Can you guys differentiate this function? Do you remember the differentiation of ln x? It's a little bit in the deep end of your brain. The differentiation of ln x is 1 over x. Like if you guys revise d dx of ln x, this is equal to 1 over x. Before, I didn't do that. Like before, I used to have u equal to x minus mu over sigma. So if you take du dx for this function, this is constant and this is constant. So this is gonna be equal to 1, right? So basically, du equal to dx, right? When we change the variable to change it from an x function to u function. But here, du is not equal to dx. If I take du dx here, this is gonna be 1 over x minus 0, and this is constant. So this is gonna stay over sigma x. So this is gonna be 1 over x multiplied by xc, and this is 0 is gonna be 0. And if I make this du, this is gonna be dx. So basically, I can take this with these two and remove them and put du. If I want to convert this function to be function in u, so this is going to be equal to, if I want to find this as fu of u, it's going to be the integration from 0 to u, and this is going to be 1 over 2 by under the root the exponential of ln x minus lambda x over xcx. This is equal to, sorry, I forgot to put half here.
Yeah.
Negative 1 over 2. Let's put them in red so you guys negative, and all this is squared. All right, so I'm gonna put negative 1 over 2, and here I'm gonna put u squared, and here I'm gonna put du. So I convert the log normal distribution to a form that represents the same solution of the standardized normal distribution. Okay? So what I'm doing here, I'm trying to convert the log normal distribution in a way that we have solution to. This function is the only integration that we have numerical solution for it. We don't have a numerical solution for this one. That's why we did a change of variables, which the variable mathematically, to put them in a function that we can integrate not in a closed form, in a numerical form, and we put them that way. So right now, this is actually represent the phi of u. So basically, if I give you like problems like the one that we were solving in a little bit, like 30 and 45. But in the compressive strengths of the concrete example, I told you that they follow normal distribution. Like after we got the data, we tried to plot the data are already normal. Like it's not log normal. But what if I told you that the data follow a log normal distribution? So rather than saying that u equal x minus mu over sigma, we're gonna say that u is equal to ln x over lambda x, minus lambda x over xcx. That's the only difference. Okay, so I'm gonna put some rules. Okay, so that's one most important equation, but the thing is, to solve this, we need to find out what is the value of lambda x and what is the value of xcx, because these are logarithmic mean and logarithmic standard deviations, not like the regular one. The thing is, when you have the data at first, like when we started solving the data, I don't know if it's log normal or a normal. So we got their mu and we got their sigma x in a normal way. But the thing is, once we plotted them, we find them that they are log normal. So we have to convert from this to this so that we can solve this function. So to convert normal and mean and normal standard deviation to logarithmic mean and logarithmic standard deviation, this is how we convert them. Lambda x is equal to len mu over 1 over the square root of 1 plus v squared. I'm going to tell you what is v in a little bit. And the c squared is equal to len 1 plus v squared. V is the coefficient of variation, COV, which is, do you guys remember?
Sigma over mu.
Sigma over mu. That's the v. That's how you convert the normal mean and the normal standard deviation to logarithmic mean and logarithmic standard deviation. And if you want to revert them, you can do some math to get mu and sigma. Like if you are given, for example, a logarithmic mean and logarithmic standard deviation, so the mean is going to be equal to the exponential of lambda x plus 1 xc squared, and the sigma is equal to the exponential of e to the power xc squared minus 1 multiplied by the exponential of 2 lambda x plus c squared. We're not going to use these two, but we are mostly going to use these two. There is a proof for this in the textbook. If you want to go and check where this is coming from, basically you are getting the expected value of lambda x, and once you substitute in this function and do all the math, you are going to find out that the lambda x is equal to this one, and the cx is equal to this one. All right. Does anybody have any questions so far?
If I have data from the beginning and I know from the drawing data that it is go with log normal shape, okay? In this time I can get the mean and standard deviation with take len of all data.
No, it's not going to work that way. It's not going to work that way. You have to use these two to get this one.
I can make.
I believe so, yeah. But you can try it. Like you can get all the len, and once you get all the len, try to take the average for them. Maybe. Yeah. All right. So, but the thing is, usually I don't give you data, but sometimes maybe, I give you a table, and you try to take the average of it. You try to take the len. But I guess maybe, if you have the data, but I usually in the exam I would give you mu and sigma x. But maybe I can give you some data that you can take the mu and sigma for them and then use these functions to convert them. Or I believe maybe if you build a table, but the way how you calculate the standard deviation, you have to calculate the expected values. And when you calculate the expected values, you have to go into equations. These functions get them in a closed form right away. Okay, so let's solve an example and see how this. Okay, so okay, our example says that the annual extreme 3-second gust wind speed is described. I don't like to write problems, but I will do it. Described by a log normal distribution with mu equal to 60 mile per hour and v equal to 0.2. I give you v right away, the coefficient of variation. Number A, I'm asking for what is the design wind speed for a structure to be designed for a 50-year event. Alright. So basically, like let me talk about the 3-second gust wind speed for you who doesn't know it. So basically, wind speed is something. Let's put here event, and let's put here the v mile per hour. Okay. So wind speed is something like this. Like the wind is very small, and then you get a gust that is very high, and then the wind is very small, and then you get another gust, and then you get another gust, and then you get another higher gust, and another one, and something like this. So the 3-second gust wind speed is events that happen in a specific interval that are average every 3 seconds. So here is something, these are the events. So when they collected this data, they found that this data follow a log normal distribution. Like all these wind speed, these events, they follow a log normal distribution. And their normal mean are 60 mile per hour, and this is the coefficient of variation. Basically, you can multiply 0.2 by 60, and it's gonna give you 12 mile per hour standard deviation. Okay, so this v, as we said, v is equal to over. Okay, what I'm asking for, what is the design wind speed for a structure? What is the design wind speed for a structure to be designed for a 50-year event? So, thing is, we need to design a structure. We need to find the probability of V50. Okay, so what is the design wind speed? Design wind speed is the design for a 50-year event. We need to find like 100, do you guys remember the 100-year event flooding? We need to find the flood depths that happens once in 100 years. Here we need to find the wind speed that happens once in a 50-year. So basically, we need to find out what is the probability of the V50 to happen. Or, and this is that mean, what is the probability of V to be more than V50? That means like, okay, all the wind speed that happen in the 50-year are less than the V50. Like the V50 is huge, like let's say it's 90 mile per hour. So all the wind speed that happen in these 50 years are 60, 70, until you hit the 50-year threshold and the wind speed exceeds the 90 mile per hour. Okay, so we need to find what is this value. And usually, when I ask you for a 100-year event, like when we say a 100-year event, that means that happened once in 100 years. So what is the probability of this event? Is 1%. But if I told you what is the V50, that means that this event happened once in a 50-year. So this probability is 1 over 50. Okay?
What?
Like from intuition, like if I told you a 100-year event, that means event happened once in 100 years.
So I just.
So the probability of this event to happen right now, like let's say, what is the probability of getting hit Miami-Dade County by a 100-year event flooding right now? It's 1% chance because it has 1% to happen over the 100 years. So it's like it happened once every 100 years. If it happens 1 every 1,000 years, it's gonna be 1 over 1,000.
So I take the probability as time, with the time. Like if it's 100 years, it's 1 over 100.
Yeah, because it happens over time. It happens in a specific year.
Okay.
And we're gonna talk about geometric distribution. Is gonna help you understand what is the return period concept. But the probability of the wind speed to be exceeded in a 50-year, that means it's gonna happen not many times. Like let's say, if you are gonna get the V50 3 times in the 50 years, that means it's 3 over 50. okay? But you are gonna get it once in a 50 year. So that's the 1 over 50. So the probability, this probability is gonna be equal to 0.02, all right? But since I told you that this follow a log normal distribution, this velocity is not, this velocity is not normally distributed. The thing is, the probability of V more than V50, we cannot deal with it. We deal with the probability of flips because this is how our distribution is. So we can say that this is also equal to 1, like let's say the probability of V to be less than V50 . Do you guys know? 1 minus 0.02. So the probability of getting V50 is 2%. So the probability of not getting V50 is the 98%. Like, what is the probability right now to be hit with 100-year flooding? Is 99% because there's 99% chance that we're not gonna get flood right now. But there's a low chance that we are gonna get the 100-year flood right now, which is the 1%. Same thing for the wind speed. You have 2% chance of getting hit by the V50, and you have 98% chance of not getting it. So this is equal to 0.98. And basically you can do it that way. Like the probability of V less than V50 is equal to 1 minus the probability of V less than V50. And then you can send this that way and send that way, and then you can find the same thing. All right, so let's take it from here. Okay, so right now we found that we are trying to find the probability of V less than V50 is going to be equal to 0.98. Since this follow a log normal distribution, so I can say that U is going to be equal to ln V minus lambda V over xc of V. That's what we have done here, so that we can solve using the numerical table that we have, right? If we're in a little bit, if we want to find the probability of x less than x, and x is a log normally distributed, this is the CDF function, and we converted the CDF function to U so that we can solve it. So if you want to find V, since it's log normal, you have to put ln V and you have to deal with lambda xc. But if I told you it's normal, so you are going to keep this as V, and this as VU, and this as xc. Since it's log normal, we have to put it that way. So U is going to be equal to ln V50 that I don't know, because I'm asking for the wind speed for the structure design for 50. That's what I want to find out. Minus lambda V, I need to calculate it over the xcv, and all this I need to find out, okay? So the V of U is going to be equal to 0.98, right? I have here the probability of V less than V50 equal 0.98. If I convert this to U, I already know the phi of U is equal to 0.98. It's kind of reversible problem. In other problems, we didn't know V, and we tried to find the probability. Right now, I don't know V, but I know its probability, okay? So it's a reversible problem. So if I go, like let's put that, let's substitute with U is equal to ln V50 minus lambda U over, actually, lambda V over the CV, this is equal to 2.98. If I take phi inverse for both sides, ln V50 minus lambda V over xcv is going to be equal to phi inverse of 0.98. What does that mean? What does that mean? That means, like, rather than before we used to go with U, like before we used to know U, and we go with U in the curve, right now I'm gonna go with the value that we get from the curve. So I'm gonna go in the curve and try to find where's the value where the probability is equal to 98%. So I'm gonna go in the table, I will find out, yeah, this is 9.7. Yeah, 9.8 is equivalent to U of 2.06. from the table. So basically, this is equal to 2.06. This is phi inverse. Phi inverse mean is the other value, right? Do you guys understand it? The phi inverse? It is like taking the inverse of the function, but here it's rather than that we know u, and we try to get u in the table from here, we know what is the value, the equivalent value of u in the table, and we're trying to find what is the corresponding u to this value. So I went in the table, tried to look for the 0.98, where is the probability is equal to 0.98%, and this is somewhere here, and this is equivalent to u of equal to 0.06. So right now I have ln V50 minus lambda V over the xc of V equal to 0.06. If I know lambda V and xc V, I can get V50. Here is the equation of lambda V, so I can put that lambda V is going to be equal to ln mu over 1 plus V squared under the square root. So this is going to be equal to ln mu is given 60 miles per hour over root 1 plus 0.2 squared, and this is going to be equal to 4.07. xcv is equal to ln 1 plus v squared, all this under the square root. So the square root is going to be equal to ln 1 plus 0.2 squared, and this is going to be equal to 0.198. So I can say that ln v50 is going to be equal to 2.06 multiplied by xcv plus lambda v. If you did this calculations, 2.06 multiplied by 4.07 plus, multiplied by 0.198 plus 4.07, this is equal to ln v50. And this is going to be equal to 4.47. Do you guys know how can I get v50? If you have ln v50 is equal to 4.47,
Take exponential.
I take the exponential for both sides. If I take exponential to the ln, it's going to give you the v50. And then take exponential, because exponential slash the ln, they cancel each other and they give you the variable. So this is going to be the exponential of 4.47, and this is going to be equal to 87.24 mile per hour. Do you guys understand this? Is there any difficulty? So basically, the bottom of this, if I give you a problem and I told you that it follow a normal distribution, like I give you the gust wind speed and follow a normal distribution, you convert the normal distribution to standardized one, and this one is going to be, rather than ln v lambda v xcv, is going to be v minus mu v over sigma v. And then you use this in the standardized normal distribution table. But if I give you the annual gust wind speed follow a low normal distribution, so you have to use ln v lambda v xcv, convert everything to logarithm. And once you convert them, then you have to go back to the table, the standardized table test, but make sure that you have the ln. So you are going to deal a little bit with some logarithms and exponentials, so that you can find the value of the final v. Sometimes you will be given, I'm going to ask directly, what is the probability of something to happen? So if I'm asking the probability, like what is the probability of having a concrete compressive stress less than 50? So basically, you are going to go to this table directly to get the values. But if I ask you, I give you the probability, and I'm asking what is the corresponding compressive stress, so basically you look for the values corresponding to the probability if you have, which is here 98%, and get the value. So it's kind of a reverse question. Okay, and by the way, this V, the V50, like the V50 year event is here 87.24 mile per hour. In the SE7, the V50 is 19 mile per hour, which is very close to this number. So it's kind of like a realistic problem. Okay, so with this, let me give you an introduction about other distributions. Right now we are done with the continuous random variable distribution, and we are gonna have a little bit of adventure with discrete random variable distribution. So here, discrete random variable distributions. So we have many discrete random variables distributions. Let's put some names. We have Bernoulli distribution. We have binomial distribution. We have geometric distribution. And many other distributions. We also have Poisson distribution. We're not gonna do it. We're gonna just check these three: Bernoulli, binomial, and geometric distributions. Okay, so let's start with Bernoulli distribution. Are you guys done this board? By the way, the wind example, we are going to continue on it next time using these distributions. So we're going to put the same example again and solve for other things. Okay. So let's put here number one, Bernoulli distribution. So what is Bernoulli distribution? This is when the distribution of X represent the outcomes from a single trial, and it's a discrete distribution that only has two possible outcomes. So when you have a distribution that only have two possible outcomes, like flipping a coin, it's either head or tail. There's no any other outcomes. So we say that the outcomes that you want, we say a success, and the outcomes that you don't know is a fail. So Bernoulli is only about fail or success, head or tail. Okay, it only have two outcomes. But the thing is, you will tell me, but that's like, I mean, like, that's easy. If we are flipping a coin, it's a 50-50. But the thing is, what if I told you what is the probability of getting a head when you flip a coin in 5 trials? That's when you have many trials, not only one trial. So when you do the same experiment, more, we need to find out what is like the probability of you are getting, for example, or having a success in 5 trials. Like, let's say the thing is, if I'm flipping a coin right now, you have a 50-50. But what if I'm flipping it many times? What is the probability of getting a success in 5 experiments, or in 5 experiments of flipping a coin? So let's put it that way. That's actually the, since it's discrete, so we are gonna deal with the probability of X equal to X. And this is equal to b to the power x multiplied by 1 minus b to the power x. So what is this? B, let's say, okay, let's say if, let's write this down, it is a discrete distribution that has 2 possible outcomes. 2 possible outcomes. And it's either 0 or 1. That is fail, and that is success. Okay? And let's say so it's either x is equal to 0 if it's fail, and it's either equal to 1 if it's a success. So the probability of you are failing the experiment, like x equal to 0, this is gonna be equal to the probability, like x is equal to 0. So we are gonna have, by the way, b is gonna be to the power 0 multiplied by 1 minus b. This should be not x, this is 1 minus x. 1 minus b to the power 1 minus x, which is gonna be equal to 0. So that probability, what is b to the power 0 is 1, and 1 minus b to the power 1 is 1 minus b. That is the probability of fail. The probability of success, so x's only have two outcomes. Either it's 0 or either it's 1. 0 means that you are failing, and 1 is that you are passing or having a success. And this is gonna be equal to, you substitute and the BMF, the probability mass function. Do you guys remember when we have a discrete, this is called BMF, probability mass function. So if you are having x equal to 1 success, so this is gonna be, you're gonna go back to the BMF and put x is equal to 1, and this is gonna be 1 minus b, and this is 1 minus 1 minus x, and this is gonna be 1 minus b to the power 0 is gonna be 1, and you are gonna be in with b, and that's a success. Which is a very simple discrete distribution. You either having, like let's say flipping a coin, to get a head is 50, so to get a tail is 1 minus 50 is also 50. And if the probability is lower than that, like let's say you are doing an experiment that is gonna give you a success 30%, so the probability of getting failed is 70%. So that's actually the rule for it. Like this is where it comes from. Like let's say that you like getting a success. Okay, so like let's say this is getting a success is 1 and fail is 0. But in the experiment that has flipping a coin is 50-50, right? So b is gonna be equal to 0.5, so 1 minus 0.5 is gonna equal to 0.5, so you are gonna have 0.5 here and 0.5 here. But let's say that you have an experiment with the success probability equal to 0.25. So you are gonna have here 0.25, and you are gonna have here 1 minus 0.25 is gonna give you 0.75. The mean and standard deviation, let's put them. Okay. The mean of this distribution is the expected value of x, and it's always equal to b. And the sigma of this distribution is the expected value of x minus mu all squared, and this is, let's put this as sigma squared, which is the variance, and this is going to be equal to b multiplied by 1 minus b. That is the mu and the sigma squared for this distribution. I put the proof for these two using the expected value formula. So if you want to know where this is coming from, I basically take the expected value of x and substitute with the information that I have here. Okay? It's like if I want to find out the expected value of x, you guys remember we take the summation and we put x here, and here we put the b of x. B of x, I have it here, and then you multiply by x, then you will find out that is equal to b. All right, let's solve an example that is not flipping a coin. Let's say that we have a data showed that 1 in 100 American is a lawyer. Okay, so it's basically we are going to find people are doctors or not doctors, people are lawyers or not lawyers, people are engineers or not engineers. So I put in a simple example because flipping a coin is kind of sketchy, like we have done it before. So let's do another thing. Let's say the probability of, or the data showed 1 in every 100 American is a lawyer. So tell me, what is the probability of being a lawyer?
1 over 100?
1 over 100. What is the probability of not being a lawyer? 99 over 100. So this is 0.01 and this is equal to 0.9. So if you want to find out the, if I want to find out this, like right now I did it with my intuition, but if I want to use this formula, because this one is the one that is going to give you the probability of x equal to 0, that's not being a lawyer. The probability of x equal to 1 means success, 0 means fail. So let's test what we have done. Is this formula actually represent what we have done or not? So this is going to be equal to b is going to be equal to 100 to the power x, which is 0, multiplied to 1 minus 100, and this is going to be 1 minus 0. So the probability, this is going to give you 1, and this is going to give you 0.99. This one, if x equal to 1, that's success if you are a lawyer. So you're going to get 1 over 100 to the power 1, and this is going to be 1 minus 100 to the power 1 minus 1. So this is going to be 0, and you are going to end up with 0.01. So the success, which is being a lawyer, is equal to 0.01, and the fail of not being a lawyer is 0.99%. That's the Bernoulli distribution. Does anybody have any question on this? That's a very simple distribution. It's either you are this or this. Okay? All right, maybe I'm gonna stop here, and next time I'm gonna continue on the other distribution and solve more examples. I would suggest that you guys start revising for the midterm exam. As I told you, next lecture is gonna be where the exam is gonna stop. So, okay.
So the next lecture going to include.
Yeah, because